Hi there, and welcome to what I believe will be the last video for the BPK 409 course. There might be one or two additional videos if we realize that something there needs to be some more additional information, but in principle, this should be the last video and this should be the ending of this course. Today, we'll talk about how we can write an algorithm, a very simple algorithm to count steps when we walk or we run. There's obviously a lot of things that I'd like to say, but I think I'll keep this for the end. And with this, let's just start and talk about the step counting algorithm. Okay, I've already set up everything, so we just need to go over the code and I'll explain step by step what is happening in my code here and what we'll have to do. So I've created a script called lab4 step count. You guys will just include this in the main code for when you hand it in on Canvas for the TA to mark afterwards. Here I have some libraries that we'll need. Like it's kind of like the general ones that we almost every time use: the NumPy, the plotting, the pandas, and the SciPy signal for the filtering. So I'm just gonna run this here. That worked. Then I have my data, the labeled data 1.csv. I have it in my working directory now. Obviously, we also have like all the labeled data here for the classification algorithm from the video before. But for the step counting, I just put it here that it's easy to import. You can obviously also import it from this folder here, just so that for the TA, it will be as simple as possible. Our column names there will be like before. We have the x-axis, the y-axis, the z-axis, we have the time, and we have the activity, which is either walking, running, standing, or lying. And for us today, it's really just the walking and the running that's gonna be relevant, but I'll show you afterwards how we can isolate those from everything else. Okay, let's run this here. And then here I basically just import the data set. Let's just have a look if everything worked out here. There we go. So we have X, Y, Z, T, and the activity here. And the first one is just, the index. Sometimes it also imports the index from the CSV file as its own column, and it creates a new index here as well. But that doesn't really change anything for us. And what I do too is, because we have time in milliseconds, I just create a new time variable where I divide it by 1,000, that I have it in seconds just for plotting, that when I say it's seconds, that it is actually seconds, not like in some videos before where the x-axis says seconds, but it's obvious that it's milliseconds and not seconds. So let's first just have a look at our data. So here I'm basically just creating a plot with two axes. One axis will be for the acceleration data, and the other axis will be for the activities. So let's go down to, let's say here. Oh no, actually, let's go down to here and just see what happens if we do this here. Like that's with the legends, the x-axis, the title, and everything. So this here is basically really just our acceleration. The acceleration from the x-axis blue, orange y, and green is Z. And then if we add the second axis here, that's what we can do with these lines here. So here we just say we want to create a second axis, and then here we say what the second axis should be. So if we run this here as well now, there we go. Then we actually have we know what was which activity from how we labeled it in the first video of lab 4. So we have the standing, running, standing, running, standing, walking, standing, walking, standing, lying, and then standing. This part of the code is really just to have an overview of how our data looks like and if we imported the data the right way. Then just for fun, we already did that in lab 1, but I also just calculated the sampling frequency. We'll need it later for the filtering. So we can also just say sampling frequency equals 25 because we know that we collected data with 25 Hertz, but I'll just actually calculate what our sampling frequency was based on the time information that we got from the acceleration data. And if we look here, we can actually see that it's not 25 hertz, it is on average 24.48, so about 24.5 hertz. That might be because sometimes there is a data point missing, or maybe sometimes it's not very accurate and so on. So, but it's really the average, okay? So the average is 24.5 here. And now what we want to do is we want to isolate our walking and running. So we don't want to work like we don't want to, okay, let's plot this here again. What we don't want to do is we don't want to count steps at the standing part here, and we don't want to count steps at the lying part here. So we really just want to have this data, this data, this, and this data. And that's where the pandas data frame comes in very handy, because it gives you the option here to basically with the df. So df is the name of my data frame of all the data, and I just call it df for data frame. So and the df.log helps you to isolate, and then you just say, I want to isolate the ones where the activity of the df is running, or so this one stays for or where the activity is walking. So let's just do this here. Okay, and we call this new variable now step data. If we now look at the step data, what we can see is that it does not start like before with standing. It actually starts with running. It will be running, and then there will be no standing in between, but just walking as well. The only thing that also happens here is that the index here starts not with 0, because the index 0 was the first one was at standing, right? And so the first running data point was at index number 1668. So I just also, just to make it a little bit easier and to make the data frame a little bit more beautiful, we do what we did in one of the videos before. We just reset the index, that the index starts with 0 here. There we go. And then also because for this here, for step data, we actually get now again the time in milliseconds, because we got it from the original one. So that's in milliseconds. I also say here, I'm kind of like taking out the step data time, and I'm calculating divided by 1000. That again, I have the time in seconds again. There we go. So we can see now here pretty easily that the walking part, or sorry, the running part started at 68 seconds. Okay, so let's have a look now at our isolated step data. So this should be now a plot. So now we're plotting the step data with its time. So the x-axis, y-axis, and z-axis, and this should actually now be a data set without the standing and without the lying part. So if we plot this here, that's how it looks like. So it completely deleted the standing in the beginning, and in between, there is just no data. So it just connects from the last running part to the first running part here, and from the last running part to the first running part here, and so on. So there's just no data in between whatsoever. That's what we wanted to do. So now what we can now do, now we can calculate the steps number of the running and the walking. So basically we can calculate how many steps we did for this whole set here, because there's nothing in between anyways anymore. So, and let's have a look at this again. Oopsie, that didn't work. So, and I said before, for this course or for this specific lab, we're trying to use a very simple step counting algorithm. Obviously, there are like a lot of very complicated but way more stable algorithms which work for sprinting, running, walking, and so on. So Fitbit and all those activity trackers have way more sophisticated step counting algorithms. But what I'm going to show you guys today is basically the it's the bare bones of how you start a step counting algorithm. So theirs is more sophisticated, but they also started with these simple methods that we will talk about today, or this one simple method basically. So if we zoom into the running data here, if we check this out, we can see that all the axes, and especially the x-axis, are very what's the word, repetitive. They're very, very repetitive. And especially here, we can probably already just do a, for the x-axis, we can probably already do just a peak finder algorithm, because we would find this peak, this peak, this peak, and so on. And if we now go a little bit closer and just try to make sense of this data, so I actually wrote it down. For this part here, the subject did 290 steps, so counting left and right foot. So when I did the classification video, I realized I told you have to count the gait cycles. It doesn't matter. If you count the gait cycles, then you just have half of the number in the end. If you count each step, left and right, you just have double the number. So it really doesn't matter what you counted. So for this one, the subject had 290 steps. So with steps, I mean he counted left and right. So if you have 290 steps within 2 minutes, that means 290 divided by 120 seconds is 2.4 steps per second. So if you look here now, we have from 190 to 120, we have about 1 to a little bit more than 1 peak here, which means that might be 2.4 per second, right? So what we know here now is, like, if we find the peaks here, that these are the peaks for each step, for the left and for the right foot. And if we think about it, it makes total sense, because we had our accelerometer on our left hand, and the x-axis was like in the vertical direction, right? And if you're running now, if you're running like this, you're basically jumping up and down with the foot all the time, and those are the peaks. So every single time you, it's probably the heel strike, no matter if it's the right or the left foot, all your body gets kind of like this impact, and that's the impact that we can see here. Let's now have a look at the walking data. And for the walking data, that's already a little bit more complicated. If we just would use a normal peak finder here, we would find this one, this one, this one, and it's just too noisy. So for the walking, that's not that easy anymore. But we can still see that this data is kind of like repetitive. So maybe by filtering it, we will get the peaks out of here as well. So let's maybe just try to filter this data in general and see what happens. So here, I now set up I prepared the filter. So we learned in lab, I think 2 in the ECG lab, we learned that what the Butterworth filter needs here for the critical frequency is a number between 0 and 1. And this has to do with the Nyquist frequency. So the Nyquist frequency is half of the frequency that we're collecting with. So in our case, if we're collecting with 25 Hertz, the Nyquist frequency is 12.5. So that's what I'm here doing. What I'm doing here is I'm calculating the Nyquist frequency, so the sampling frequency divided by 2. And then, so if I want the critical frequency, like the critical frequency is the cutoff frequency, and we want low frequencies to pass, because we want to get this like low frequency repetitive movement. I want frequencies under 3 Hertz to pass, right? But because it has to be a number between 0 and 1, we're calculating 3 divided by 12.5 or whatever, which is 3 divided by 12.5, something around 0.25. And that's going to be the critical frequency in our Butterworth filter. So here we're basically preparing our Butterworth low pass filter. Okay, and then we're filtering, and since we have talked about looking at the x-axis, we don't need this part here, and we don't need this part here. So let's filter our x-axis. So I call it x filter. It's filtered here. And let's maybe just plot this. I don't have that in here yet. So LPLT plot. And then let's say x filt. And maybe let's also say, what do we call it? Step data time. So we have the time on the x-axis. So let's have a look here at the running data. So the cool thing is this, because the running data didn't have a lot of noise, the running data just basically stays the same, which is very good for us because we can still just go for the normal peak finder algorithm for the running data. And if we look at the walking data, here we go. So the walking data seems to have those two peaks, like kind of like always, right? So and if we now zoom in here, just that we are able to like think about this a little bit closer. So if we look now from 515 to 455, oh my God, 515 to 514 to 515, we have kind of like two peaks. But if we like just move on here, like we can see it's probably a little bit less than 2 peaks per second. And if I look here at my data now, what I collect here, so I did 222 steps, so counting left and right, 222 steps in 2 minutes. So again, 222 divided by 120 seconds is 1.85 steps, or 1.85 steps, or peaks in that case. Those are the peaks, right? 1.85 peaks per second. And again, that kind of like makes sense, a little bit less than 2 peaks per second, right? So, and at walking, we'll probably have our hands like a little bit more hanging. So it's more about the back and forth movement. But the reason why we have those 2 peaks, and I'm just like, I'm more shooting in the dark here, but I guess it's not just the swinging, but it's also the braking and accelerating every time you do push off with your foot. And that's why we have 2 peaks, and then once where it goes further down is like then the swinging as well. I guess that's my explanation for this. If you actually know the literature about that, please let me know in the comments, and maybe I'll do an extra video to tell people what's the actual truth and not just shooting in the dark and saying what I think it is. So cool. So now we have those 2 peaks here, and for the running, it looks good as well, right? So what we now want to do is we basically just want to use our peak finder function that we've also used already a few times before to find those peaks. And okay, we also don't need this part here. And now we can just have a look if that worked. If we now plot basically the filled data, and then with this line, I'm also making an X at the peaks that it calculated. Then, oopsie. So turn this, there we go. If we zoom in here, that worked pretty well. Obviously, it's not perfect, but it worked. I mean, here it actually looks pretty perfect, to be honest. But then, yeah, we can see here that there are some peaks. Like, yeah, that was probably a data collection problem or something like this. So that one works pretty well. And then the same for this walking part here. That one looks good too. And then here I walked actually a little bit faster. So it looks, the data looks kind of different. And that kind of like makes sense because I walk faster, I'm probably swinging my arm faster too. So the one peak when I'm swinging is higher, but the other peak of the push off of the second foot is still there and it still works. So our algorithm is still working. So what I want you guys to do now, that's basically it with my explanation today. What I want you guys to do is now is look at your data and think about what would make sense. Like it might be that the x-axis works as well as it does for me. You might have to play around with the critical frequency a little bit. Always plot as much as possible and see what's going on in the data and if it works or not. Then also having a look at the y-axis and at the z-axis, maybe in the y-axis or in the z-axis, there is some repetitiveness as well that you could use to count the steps as well. And then in the end, we want you guys to compare the algorithm with what you actually counted. So in that case now, you would also, so what you need to do as well is you need to isolate this part here and count the peaks. How many peaks did this running part have? And compare it with your own number that you counted while running, right? You then do the same with this here. Just count the peaks of this part, just count the peaks of this part, and just count the peaks of this part. I'm sure that by now you guys can figure out how you can just isolate the first running part or just isolate the second running part, and so on. I'm not sure what's something else that I wanted to mention here. No, I think with this, we're actually done for the step counting video. Like when you have this, you can compare and you can calculate the accuracy of your algorithm, and then that's basically it. If you guys want to go a little bit further, like there are different ways how you could do step counting as well. Like you could use some of the knowledge we gained in the ECG lab to find the peaks there. So you might want to work a little bit like with the differentiated signal. You might have higher peaks before the peak and so on, and the different ways, but this is the most simple way to find the peaks and to do a step counting algorithm. Very nice. So at this point, we're done with the lab 4, and I think that's actually now pretty cool. Like we built in the very beginning, we built our own fitness tracker. We did some data collection, and now you learned how to write the code for the bare bones of a fitness tracker. So on the one hand, it is classifying which movement that you're doing. And then when you have classified what is walking and what is running, you can then as well use your algorithm that you wrote yourself as well for counting the steps. And that's basically how the first fitness tracker started. And that's basically how it works. Obviously, obviously now the devices are way smaller. Everything gets put into like a way smaller device that one basically watch here. And the algorithms are way more sophisticated. They have way more classification, like they have more data, that they are more stable. They are also have way more activities. Like in our cases, we have 4 activities. They have way more activities, and their step counting algorithms are already way more accurate because they have, on the one hand, more data, on the other hand, more sophisticated algorithms and so on. But you learned how to build and code the first part of a fitness tracker in general. With this, we're not just at the end of this video or at the end of this lab, we're actually at the end of the whole course and of all the lectures that we did for the specific BPK 409 wearables course. As I said before, there might be some additional videos at some point, and obviously within the next semesters, there might be some new equipment coming in or new lab starting, and we might add something the next semesters. But for this semester, which was the very first semester, which is for the people watching this video a little bit later, is fall 2020. That was the very first time that we did this course, and that's the last video of this specific semester. I want to say thank you to everyone. Thanks for being patient. Obviously, because of COVID, we didn't have a lot of time to prepare this whole course. I believe that it worked out fairly well. I hope that you guys learned as much as you wanted to learn. If you think about what you did before when we started with this course and how far you have come afterwards now, I guess like you're able now to measure EMG, to analyze EMG, you're able to measure ECG, to analyze ECG, you're able to doing some acceleration, data collection, and now even doing classification, activity recognition, step counting, and so on. And if we think about this, we all started with this one simple device, and I think that's incredibly amazing. We started with a small device. Some of you guys have used this before, some of you guys didn't, and now this one device led you to using it for all those different things that I just mentioned and even more. And a lot of you guys did, or all of you guys did the project in the end, also with this device. So I hope that you started to appreciate a microcontroller and the electronics as much as I do. I think it's amazing, especially for piloting projects, for piloting equipment and so on. This is a perfect piece of the advice. No matter if you're at academia and you just want to do like 1 study, 2 studies, you can use it. But also if you're in industry, if you want to build a new device, that's where you will start. And once it's working, the code is working and so on, that's where then you'll put all the things into one device together. yeah, with this, again, I want to thank you guys for your patience. I'm super looking forward for the next semester. It might not be me anymore teaching it, but maybe I'll add some videos. And if you have anything that you'd like to let me know, please put in the comments, email me or whatever. And we're always looking forward for some feedback. Maybe you have some feedback as well for videos that we could add or for things that we could clarify a little bit more in some videos. Let us know. And with this, I hope you had as much fun as I had. And I hope I see you guys soon eventually. Take care. Bye bye.